everyone, welcome to this video. Today we would like to show our work on algorithm approaches on searching optimal parking location. First, I would like to provide an introduction on why we choose to work on this project. Nowadays, people are experiencing headaches due to parking issues in the city. Searching for a best location to park is one of the most challenging tasks during leisure travels to heavily populated place, daily commute, and other events. Our team wants to apply algorithms that we learn in algorithm class, such as Bellman-Ford, Dijkstra's algorithms, Floyd-Warshauer, to help people easily find the optimal parking location that best suits people's needs using Northeastern University network as a study case. An ideal parking space would be easy to find with low parking cost and short walking distance to the destination we want to go to, and ideally also have a short driving distance from current location to the parking slot. So in this project, we convert the path network at Northeastern University into a graph in order to apply algorithms to solve this problem. In this slide shows approximate graph of the Northeastern building network. Orange nodes are parking garages at Northeastern University, purple ones are other parking space, and green nodes are the campus buildings. The ultimate goal of this approach is to find where I should park if I want to go to one of the places at Northeastern campus as my destination, and how this graph is created. I create this graph with edges based on the main road and paths that connects campus buildings. The walking distance between buildings is Euclidean distance in miles if they are on the same road or lanes and they are next to each other. And there will be no direct edges between buildings A and B if I have to pass through any additional buildings to reach from A to B. The first analysis of this project focused on finding a close parking spot with an easy walking route. For people with bad sense of direction, they may want to go to some place that not only near the destination but also easy to find. The road with the shortest walking distance may not be the best solution for me. If the road is too complicated, I need to turn left, then right, and then left, right. Okay, I'm lost now. Instead, I would choose one with simpler road in terms of total number of turns that I need to take, and even I need to walk slightly further. So as you may remember from the previous slide, building is connected by edges. So if I want to use number of edges to represent number of turns that I need to make sure all the buildings on the same side of the road are directly connected with single edge with updated weight. So for this reason, I applied Floyd-Warshauer algorithms to find the pairwise distance between the buildings on the same side of the road. So buildings on the same side of the road require 0 turns. Then I can apply Bellman-Ford algorithms to figure out if the buildings can be reached from any parking slot with at most k edges, and report the parking slot with the shortest walking distance as the optimal parking spot. If you are not familiar with these two algorithms, feel free to check the Wikipedia page by clicking the hyperlinks. Network flow at Northeastern campus is not too complicated, so most of the places can be reached using at most 4 edges. The optimal solution for parking will not change even I increase limit on turns to 5. The table on the right shows the optimal parking spot for selected destination at Northeastern University with limits maximal turns from 1 to 4. So for example, if I want to go to Snell Library but I can only accept 1 turn, then Belvedere parking garage would be my option. But if I would like to accept more turns, then Columbus parking garage would be a better option. This image is too small for me to include all the information, so if you are interested in the Northeastern campus layout and the ideal parking route, you can click the Northeastern map hyperlink below to explore more. For the ideal parking location, we want to reach a balance for the driving distance and walking distance. However, if I make judgments based on the total times it would take me to go to destination from my current location, I would always pick Columbus Parking Garage for Snell Library instead of the image that you see on the left that is just based on the driving distance.
In this analysis, we apply Prim's algorithm to find the shortest path that connects multiple locations. With the input as the pairwise distance between buildings, we construct a graph that only contains the edges that connect destination nodes and edges that connect the optimal parking slot for each of the destinations as shown in the below graph. The key is to use Prim's algorithm to find the minimum spanning tree for the new graph. The following shows an example of the optimal route. For example, if I want to visit the Snell Library, Curry Student Center, and West Village Hitch, the ideal way is to park at the West Village parking garage and then go to the Snell Library, then Curry Student Center. The Prim's algorithm has successfully found the optimal route and parking spots when there are multiple locations that we want to visit. It reduced the time complexity of the problem when we reduced the full graph to the subgraph that only contains the edge from destinations to each of its parking lots and edges that connect the destinations.
Hello all, the topic of this project is parking space suggestion based on shortest driving route, shortest walking route and price. The shortest distance has been calculated using Dijkstra's algorithm. The problem statement we are trying to solve is suggesting the parking space to the user who wants to travel to a particular building within Northeastern campus based upon the price, the driving distance from the user's location to the parking space and walking distance from the parking space to the final destination. Moving on, I'll be showing you how we have collected data to work further on this idea. Initially, I have created the driving route map or graph of the Northeastern campus and its surrounding. For that, I have considered Northeastern as the midpoint and I have taken a radius of 800 meters around it. The final output is what you are seeing on the right hand side of the screen. This has been implemented using the OSMNX module and NetworkX module of Python, where the edges are the streets and the intersections are the nodes. These edges have been color coordinated, as you can see, where deeper color are the ones with the longer length and light colors like yellow is the shorter length. This graph which you are seeing on screen is the walking route of the area of the Northeastern campus and around it. We will use this graph for calculating the walking distance from the parking space to the final destination, while the previous graph was used to calculate the driving route distance from the driver's location to the parking space. This has also been created using OSMNX and NetworkX, and the color coordination seen in this graph is similar to the one which we saw previously. The pandas data frame which we are seeing on screen is the Northeastern buildings and their respective latitude, longitude and the node on the graph. This will be talked further about by my teammate Charita. After collecting the driving and walking route network of the campus and its surrounding, now the time is to calculate the parking space available in and around the campus. For this, we have used the website called Parkopedia's data. Basically, we scrape Parkopedia website's data to get the parking space in and around the campus, specifically 400 meters along the radius of the campus, and the specific price of this parking space for 2 hours and the coordinates. Using the latitude and longitude found from the Parkopedia website, we have used our OSMNX inbuilt module to find the nodes of this particular location in the graph which we created using the same module. So this is the right hand side in the pandas data frame has been added after calculating the node. And the final two inputs which we require for our idea to work is the user location and the user's final destination. For that, we have assumed that the user location is situated around Windsor Street and that person is wanting to travel to L Hall, whose respective node has been mentioned on the screen. The working of the Dijkstra's algorithm will be explained by my teammate Charita. Now that we have all the data required to work on the Dijkstra's algorithm, we have used the source and the endpoints to calculate the distances, and then we are showing you the final output on the screen, where you are seeing the parking spaces along with their driving distance and walking distance and their prices for 2 hours. which has been calculated assuming that the user is at Windsor Street and the destination is L Hall. So basically for the driving distance, we assume we have taken the source as the user's assumed location and the destination as the parking space. And for the walking distance, we have assumed the source as the parking space location and the destination as L Hall. And price has been scraped from Parkopedia's website. Thank you.
Hi, as Shweta mentioned earlier, we are taking the coordinates of each building and parking lot and of Northeastern University. The coordinates like latitudes and longitudes are taken from the Parkopedia website and collected the parking lots available around 100 meters. And in this, a user will be choosing a location, for example like Snell Library as his destination, and also we consider 4 locations by default, and from that location to this destination we will find the shortest path by using Dijkstra's algorithm. This Dijkstra's algorithm has been implemented in the parking system. The way that has been used is determine the distance via pathway. The algorithm used is the minimum value between 2 points. The algorithm finds the shortest path between the nodes and every other. It also uses it to find the shortest path for a single node to the single destination node. By stopping the algorithm once the shortest path to the destination node has been determined. So here we have I have already said like we have taken the starting point and a destination which our user chooses as an input, and next we are assuming the node to be the end point and checking if the node is equal to the starting node. If it is so, that we are appending it and updating the node to the previous node. So next we get the costs of the nodes. So next we initialize the distance from the starting node, and with the elements are in the sorted tuple and distance from the starting node is said to be 0. So next checking from the correct adjacent nodes, and we are updating the distance for each and every edge which we are applying Dijkstra's algorithm, and finally it returns a shortest distance. So this parking, I conclude that this parking system used modification of Dijkstra's has been successfully developed. The system has provided more convenient parking system for the user. The users are able to park their vehicles at the nearest parking lot of the Northeastern University without searching for it. Based on its system, it's provided that the system has provided a convenient parking system to the user. So the driver doesn't need to waste their time for searching for the parking slot for the Northeastern University, and this makes a more this is so advantageous, and it's more efficiently used by the people. Thank you.